curve that has a radius of 105 meters is banked at an angle of theta equals 11.0 degrees. If an 1100 kilogram car navigates the curve at 65 kilometers per hour without skidding, what is the minimum coefficient of static friction, μs, between the pavement and the tires? So let's draw a quick kind of picture. We'll say the car is going like this. And let's say that at the moment we're talking about, the car's velocity is into the page, and it's 65 kilometers an hour, which turns out to be 18.1 meters per second. So we'll keep that in mind. And we know that the radius of the curve, which was given to be 105.5 meters, and we're given that theta is 11. So our first thing is to see which way this car is going to go. And we derived earlier in the class, much earlier in the class, that the critical speed is root GR tan theta. This turns out to be 14.1, which means the car is going faster than it needs to go around the curve, which means it's going to, in the absence of friction, it would drift higher up. That's going to be important because now we're going to talk about drawing in the free body diagram. So we draw, we draw a dot, and let's sketch in the incline, and then we draw our forces. Certainly, as always, let's start with gravity, and then there'll be a normal force, which is perpendicular to the incline. And then our key bit from here is that it would tend to slide up the incline, so the frictional force must be down the incline. So something like that. And then, of course, although not part of the free body diagram per se, we know that there'll be a horizontal acceleration like that. In this case, we'll need to balance all these forces, and they're kind of annoying because we have 4 vectors. We have 1, 2, 3, 4 vectors, but no more than 2 of them can lie along a perpendicular set of axes. So either we have the weight and the acceleration, or we have the normal and the friction. And whichever ones don't lie along axes, we're going to have to break up. So we're going to have to do at least 2 vector resolutions. That's sad. The general thing is that we probably want one of our axes to point along the actual acceleration. I'll call that plus x. And then the other should be perpendicular, so I'll call that plus y. And then what we want to do is just write out our Newton's law equations in both x and y. So the net force in the horizontal direction, the net force this way, well, notice that we have the normal force, which points a little bit over, I'll call it F and x, and a little bit up, I'll call that F and y. And we have the frictional force, which points a little over. That was badly drawn. So something like that. And that would have an FFX and an FFY, like this. And so looking at our x component parts, we would have FNX. And then we also have, of course, FFX. But let's see, they both point to the same direction, so we can add them. And then they should equal m times the acceleration, the x. If we look at the next thing, if we look down at the other, for the y equations, we have f and y points up. We have an fg, and we have an ffy. But we have to be careful because fg points opposite to f and y, and ffy points opposite to f and y. So they should come with minus signs. And that equals the mass times the acceleration in the y. We can make this a little bit easier. We know that the accelerations, let's go here, this is going to be v squared over r, and this is going to be 0. So we'll be able to make things a little bit simpler. What's going to be a little bit more annoying are the components f and x and f and y and so on. So let's go get those components. Here we're going to want to try and get our angle into our triangle somehow. And remember that we've drawn our incline such that this angle is theta. But we can see that that angle is the same as that angle because it is an alternate interior angle formed by parallel lines. And so then we consider that angle compared to this one, and we see that they're complementary because they form a right angle. But then finally, maybe most spectacularly, we get that this angle has to also be theta, because this angle is complementary to that angle, and this angle is complementary to that angle. So from there, we can say something like fnx over fn is the same as the opposite side over the hypotenuse, which of course is the sine. That tells us that fnx is fn sine theta. And fny over fn, which is the adjacent side over the hypotenuse, well, that's always the cosine. So fny is fn cosine theta. Things are easier for the frictional force because, remember, this is the angle from the incline, and we see sort of right at the end, because, again, parallel lines make corresponding angles equal, that this is theta. That's straight up easy. So we have ffx over ff, which is the adjacent side over the hypotenuse. So that's going to be cosine. So that ffx is ff cosine theta. And we'll have ffy over ff. And we can see that that is the opposite side over the hypotenuse. And so we're going to get sine theta. And thus ffy is ff sine theta. Finally, we know we're in the critical case, so the frictional force should be at its maximum possible value, so the frictional force is going to be mu times the normal force, and we'll put that in together as well. So to recap, we have these equations, which is the constitutive equation for friction, and then the x F net equals ma, and the y F net equals ma, and then they become the following equations. But here we're now going to take this equation and plug it in as well. And all that we've done is replaced ff with mu fn, so nothing new here. But notice now we have lots of fn's, and they're appearing in all the terms on the left, so we can factor them out and get a somewhat simpler thing as well. And then a trick that happens a lot is when we have the same factors on top and bottom, it can be useful to do a division, because equals divided by equals are equal. So I'm going to divide this equation, and I'll divide this equation at the same time. That allows us to then cancel out fn over fn is 1, and m over m is 1. And so we're left with the following single equation. Sine of theta plus mu cosine of theta over cosine of theta minus mu of sine of theta is v squared over gr. And let's highlight the things that we know. So we were given the v, we were given the r, of course we know g, and we were given the theta, so we have all the trig functions. And we see that we have a thing which is one equation with one variable, mu, and so we just need to solve it, quote unquote, just solve it. It's a bit gory, and there are two ways to do it. One would be algebraically, and that will be made a lot easier if we make some helpful substitutions. So let us, let's block this off for a sec, and let's make the following useful definitions. Let alpha be sine of theta, let beta be cosine of theta, let gamma be v squared over gr. And I'm doing that just because it's going to make my life easier to write stuff out, because now my equation is going to look something like the following. It's going to be alpha plus mu beta over over beta minus mu alpha, and all of that's going to equal gamma. That has done nothing for me except that it's less letters to write, less carrying sines and cosines and so on. Now I have to do regular standard algebra on it. So we cross multiply, and we have alpha plus mu mu beta equals gamma times beta minus mu alpha. And then we might want to distribute. So this is gamma beta minus mu gamma alpha. And this is still alpha plus mu beta. And then we're going to bring this one over here. And we're going to subtract off alpha. And when all is said and done, we're going to end up with something that looks like mu beta plus mu gamma alpha is, and then over here we're going to have gamma beta minus alpha. And then we're going to factor out the mu, leaving us with beta plus gamma alpha over here. And then we're going to divide out this, so we'll end up with mu equals gamma beta minus alpha over beta plus gamma alpha, which now we can substitute back our things, and we have craziness of v squared over gr times cosine of theta minus the sine of theta over v squared over gr, oops, sorry, take that back a bit, over cosine of theta plus v squared over gr sine of theta. And you can see why the substitutions helped in doing the arithmetic, because that was just terrible. But if you grind all of our numbers out, you would end up with 0.117. Ta-da! And you can see it's kind of grungy algebra. There's a different way to do the grungy algebra, and I'm going to show that on the next screen. The other way to do it is to recognize that we had the following equation: sine theta plus mu cos theta over cos theta minus mu sine theta equals the centripetal acceleration, which we could compute because we had v and r. And so we could go to some place like Desmos and we could plot this thing on that axis. Actually, in fact, let's do this. This thing on as that, and we could plot the other thing here, and then they will intersect at that space. And we can see that that gives us a value. Oops. A value of 0.1168, which is the 0.117 that we had before. And so that's a way of avoiding all that terrible algebra. If you're going to do this in Desmos, you have to actually replace mu with Desmos's x to make this work out, which is unfortunate because the symbols don't agree. But other than that, it's pretty straightforward. All right, and there we go. It is a thorny thicket of terrible algebra after some relatively quick physics, but I guess for completeness, there it is.